So in the last lecture, we were discussing the perceptron model, right? What type of a model is a perceptron? What is the type of the activation function which is used? What is the activation function? Which activation functions go along with perceptron?
What's
Unipolar
the
and bipolar.
yeah,
Unipolar and bipolar? Binary, right? So binary activation functions. The type of the output of the neuron is binary. The neuron is binary in nature. Give you a 0 or 1 or plus 1 minus 1 kind of an output, right? So perceptron model uses unipolar or bipolar binary activation functions. So what is the delta W value for the perceptron? What is the weight update equation?
CRX.
CRX. So for in case for perceptron, we wrote a simplified weight update equation, right? Do you recollect that?
CX, that conditions na plus minus 2 CX.
Plus or minus 2 Cx if it is unipolar. In the case that it is you are using unipolar, it is plus or minus Cx. Otherwise, it is plus or minus 2 Cx. That means when you're using bipolar binary, it is plus or minus 2 Cx. And how do you decide whether you use plus or minus? Which
it
variant?
depends on the desired output.
Correct. So it depends on the desired output D. Sign is dependent on D, desired output. Okay. So if D is plus 1, then, and of course, the weight update will be done only when D and O mismatch. Only if the network has predicted something wrong, then only you'll update the weights. Otherwise, it will be 0. So if D is a plus 1, then it will be plus 2 CX if you're using a bipolar binary activation function. Otherwise, it will be minus 2 CX if D is minus 1. In the case of unipolar, the possible values of D are 1 or 0. So we'll use either plus Cx if D is 1. If D is 0, it will be minus Cx. So this is important, the weight update equations for perceptron. Okay. And then we solved two problems on perceptron. One was a simple problem where we just applied this rule, the weight update rule, and we computed the training for each input pattern which was presented. The other problem that we discussed was where the final weights after training were given, and we had to go back, we had to backtrack and compute the previous weights. So we just rearranged the weight update equation and we could do that, right? So this was what we discussed in the last lecture. Let us move ahead today. So today we'll be looking at perceptron and the role of the bias term. So there is one term which is used in most neural networks, and that is the bias term. We will be solving the perceptron along with the bias. So the problem that we have seen so far, I did not talk about the bias. Although it was present, I did not talk about the bias. So we'll see if the bias is not present, how we have to introduce it and we have to solve the problem. So that is what we are going to do, one problem on that. And then quickly we'll go through the activation functions which are there, just so that we just have everything in uh, our slides for reference later on. Because so far what we have done is we have directly used them. We will now see the equations and the graphs, how they look like, the activation functions. So when we talk about the perceptron, this is a perceptron model. So there's a neuron, and then you pass it through a step activation function, and then you get the output. Perceptron, whatever is the net value. So what is net? Net is nothing but weighted sum of inputs, right? So you compute the net values, you pass the net through an activation function. And the activation function in the case of perceptron, as we discussed just some time back, is either unipolar or bipolar binary, which is a step function. So let us assume that we have to solve this problem which is given. Okay. So for solving this problem, by the way, what is this problem that we can see? Which problem is there? This is the AND problem, right? This is the truth table for AND, right? So let us first just try to visualize these patterns. So these are the patterns. So if you consider each row of this particular truth table, each row is a pattern, right? Each row is a pattern. There are 4 different patterns that we have, okay? 2-dimensional. So 2 features are there for each pattern. That is, each pattern in this table, it is represented by 2 features, okay? And this is the expected output. This column is the expected output, right? So that means this tells you that these 3 patterns belong to some class X, and this belongs to a class Y. These 3 patterns belong to the same class, and this pattern belongs to some other class, right? So let us visualize this on a plot. So this is the plot of this particular problem. So there are 3 patterns which we have plotted here. So x1 and x2 are the axis, the features x1 and x2, right? So the first 3 rows are 0, 0. This is 0, 0, right? This is 0, 1, and this is 1, 0. Okay, they belong to the same class, so we just represented that by a circle. These 3 belong to the same class, and the 4th pattern, that is 1, 1. Okay, this pattern belongs to some other class. Okay, so now if we want to classify these patterns, okay, what we need to do is we need to find the equation of a line. So what we do in case of the perceptron is we simply take the weighted sum of inputs, that is the net. Net is nothing but the weighted sum of inputs. Okay, a weighted sum of inputs in this case is nothing but W1 x1 plus W2 x2. Okay, so we need to find a separator, actually a separating line, which is actually going to classify these patterns. Now if we consider, if we just consider these 2 inputs, the existing input features which are there, then we can observe that this particular line that is there, that this equation that we have written, it is a line which is passing through the origin, isn't it? It's a line which is passing through the origin, right? What is the equation of this line? So suppose you want to find out this is the equation, right? So there is no intercept in this particular line. There is no intercept term, right? So using this line, if I try to solve this problem, I will not be able to solve this problem. Why? Because, you know, ultimately that line, what that line has to do, suppose this is the line that I draw. Suppose assume that this is the line that you draw. Okay. This line actually has to classify the patterns into 2 areas. So maybe this towards this side of the line, you have one particular class of patterns, and to the other side, you have the other class of patterns. Okay. Such a line, in fact, any line which will pass through the origin will not be able to classify these patterns, right? Okay. So That is where the bias comes into picture. Okay. So bias is nothing but you add one more feature. So to the existing features, you add one more feature which actually acts is this intercept. Okay. So there's an intercept, y-intercept. So you don't you want to avoid that line which passes through the origin, because your problem might not be such that every time you will have such kind of patterns which will conveniently be classified by a line which passes through the origin, right? So basically the line which passes through the origin with it, intercept 0, and this is the slope of that line, will not achieve the classification. And in order to achieve that classification, right, so that line in fact will be somewhere in between here. You need to add that intercept. You need to add that intercept to the line, and that intercept is nothing but the bias. Okay. So I mean, there could be n number of lines here, like in this region. This is the possible region, right? This is the possible region where any line that can be drawn in this region will separate the patterns. Okay. So only thing is you cannot achieve the separation with a line which passes through the origin, and that is why you need a bias. So bias is just going to shift the line. So if the line you draw it here, you just shift the line so that accordingly at one point after training it is placed in such at such a junction that it will classify the patterns. So it will be able to classify the patterns. So that is basically the role of the bias. Okay. So the equation now it comes out to be this: W1x1 plus W2x2 plus B is equal to 0. B is the bias. Okay. Now this bias, how do you introduce this bias into the neural network? How do we introduce? So we already have our neural network. We have the features. We have the features of inputs which are connected to the neuron via the weights. Right? So how do you introduce this into the network? So that is what we have to do in our network design. To introduce this into the network, basically what we need to do is we just add one extra feature. Okay? Extra feature in addition to the or already existing features for that problem, you add one extra feature always by default. That feature will have a value of 1 or -1 typically. Okay, the input, and the weight of that bias will be a trainable weight which you will compute. It will be an adjustable weight which you will compute. Every time that you're training it, you're going to update that weight so that you are changing that value. Okay. So what you're doing is this particular B term that you have, in fact, you can write this term as W1x1, this equation as W2x2 plus WB, okay, where B is 1. It's a fixed input. It's a fixed input. And what you're doing is you're making this weight, this coefficient of B as a weight which you're going to adapt, which you're going to change via your weight update. Okay, so that will help you to actually align that line finally to a position where it is going to be able to classify the patterns. Okay, so that is the bias. So that is how you introduce the bias into the problem, into the network. Okay, so this is one more example which actually shows the bias. So the patterns are somewhat different than the previous example. So you can shift the bias. I mean, that line can be shifted anywhere. It could be at the origin if it is able to classify. So in that case, the weight will be 0. The line is passing through the origin. That means the weight that you have introduced, that will be 0. Okay. So if you have a problem given to you, which you are required to solve using Perceptron learning rule, okay, and these are the input vectors. So you notice here that there is no bias term. There is no bias here because bias is a fixed term at the end. In fact, all the problems that we saw solved yesterday, both the problems that we solved yesterday, you'll notice that the last input was a -1. The last input was a -1, that was a bias term. So that is why I did not bother about telling you to introduce the bias there. Okay? But whenever you have such patterns, you always work with the bias. You always have to add that input. So if these are my patterns, x1, x2, x3, x4, and desired outputs are given, when you actually formulate this problem and start solving it, what you need to do is you need to introduce that input, the third input feature here, that is a bias. Okay. So this problem, there are 4 patterns. There are 2 features in each pattern, right? 2 features. So you will add one more bias to it. So your patterns now will become, so it was 2, 2 earlier, so it will be 2, 2, 1. Okay. And initial weight vector is given to be 0, 0. Initial weight vector is given to be 0, 0. Now what you need to do is, since you have added the bias, initial weights also, for the bias also, you assume it to be 0. It is not given, you can assume the initial weights as 0. Okay. So starting with a 0 bias, then maybe if there is a problem and it is required to shift this line, then that weight will automatically change. This WB will automatically change. So we are calling it WB, right? B is the input, bias input, WB is the associated weight. So what do we need to do? The same procedure. Only thing is now we have an additional input that we have put in here. So quickly we'll solve this problem. So 2, 2, 1 and 0, 0, 0. What is the net value? Net value is
0.
0. Now which activation function we are using here? That depends on D values. Which activation function?
Unipolar.
Okay. So what is the value of O? O is 1. Okay. Greater than or equal to 0, O is 1. Now there's a mismatch. Net is greater than or equal to 0, O is 1. There's a mismatch. So we will update the weights. The equation will be minus Cx. Okay. So C is given to be 1. C is given to be 1. Okay. So it's simply minus x. So it is -2, -2, and -1. Okay. Now you add these 2 weight vectors, you will get -2, -2, -1. Right? Again. So you see now the weight has changed. Because there was a misclassification, it's causing this weight to change. These weights have changed, obviously. This is also changed. So you're getting some coefficient for the bias. Okay. Now, net value for this, -2 plus 4 is +2 minus 1 is 1. And so O will also be 1. These two are same. So no change. Right? No change in weights. Next, the weights will remain same. Okay, compute net value. -2 into -2, 4, -4, -1. Correct? Net value is -1. What is O? What is O?
0.
O is 0. Okay. So again, it's matching. These two multiply these two vectors. So 2 minus 2 minus 1. Again, you're getting 0. So there's a mismatch. So you update the weights. This time, what is the weight update? It is plus Cx. Okay, because sine of t, it's 1. D is 1. Okay. So weight update, it's delta W is going to be equal to X. Exactly, right? So now what do we have? Add these two weights. It is minus 3, minus 1, 0. Right? So we have, again, now see what's given in the question is you have to perform 2 iterations. Okay. Now see, in the question, if it is mentioned perform 2 steps. Steps means individual patterns, steps. So I've written here step count, step number, right? Second column is step number. When it says iterations, you should understand it is an epoch, right? So epoch means all patterns are given. So this question, they have mentioned 2 epochs. Solving perceptron problems are easy because the calculations are very simple. When you are having a sigmoid and the other function, sigmoid function, then in that case, the calculations will get a bit tedious. So you have to be careful. So this net value, what is the net value? Minus 6, minus 2, minus 8, right? Minus 8 plus 0, minus 8. So O is going to be 0. They are matching. No weight change. Weights remain same. Multiply minus 3 plus 2 is minus 1. Right? So now they are not matching. So you need to update the weights. So update the weights. What is the equation? It is plus Cx again because t is 1. So it is simply equal to x. Delta W is simply equal to x. Okay. So add these two weight vectors. You will get the new weight vector, that is minus 2, minus 3, and minus 2. Right? Minus, correct? This was 0.
1 I have only.
This
Minus
is
2, minus 3, 1.
this is 1. Okay. Multiply these two. What are you getting as a net?
Minus 1.
Minus 1. Put a 0, no change. Net value for this, 2 minus 3, 0. Output is 1, same, so no change. Okay. So this is how you move ahead. You have to add the bias. Whenever the bias is not mentioned, it's not given. You look at the patterns. You look at the patterns and you check whether the bias term is there or not. If it is not present, you have to add the bias. Okay. Next, we'll see one more problem based on a perceptron. That is the apple banana sorter. So what is this apple banana sorter? So consider you have to design a network to sort two categories of fruits, okay? Apples and bananas. So there are apples and bananas. You have to classify those fruits using your neural network. So for that, first of all, we need to identify what are the features that are going to be used for representing each of these categories. Right? So how do you represent an apple and how do you represent a banana? Okay. Now in the real world scenario, there'll be some feature extraction technique. Okay. For simplicity, we'll just assume some features, okay, which are there, uh, which will describe the fruit. So the features that we look at are shape, weight, and texture. So if the shape of the fruit is round, then shape can be round or elongated. Let us assume two types of fruits only we are considering right now. Okay, round or elongated. So if it is round, then the shape input will be 1. Okay, otherwise it will be -1. So these are there'll be some sensor basically to actually detect these features. Or whenever if you're working with images, for example, then you'll have to perform some feature extraction technique to get the features. How that depends on how you're representing it. Each input pattern that you're giving to the network, how are you going to represent it? Okay. If you're looking at an image, then how do you represent that image? Now you will talk, if we talk in terms of the modern day networks that we have, like CNNs, you will directly give the image based on some resolution. You will directly give the image, and then maybe you will stack it later on. There will be some operations which are going to do the feature extraction. Traditional way is you give the features, you extract the features at the beginning and give it to the network. So whatever we are talking about right now, it is that the features are given at the beginning. So you have the fruit. First, the feature extraction is done, and then that is presented to the network. Okay. So shape, weight, and texture. So second is weight. So weight, if it is say less than 100 grams, then it is a +1. If it is greater than 100 grams, then it is a -1. Okay. These are some rough values that we have assumed. And texture, if it is smooth, then it is a +1. Otherwise, it is a -1. Okay. So how do you represent an apple using these three features? So you'll be representing it. Shape is shape, weight, and texture, if this is the order of the features. Okay. And what is the last term? Right, this is x1, x2, and x3. Last term is the bias, because we are going to use a perceptron to model this, right? So x1, x2, x3 is 1, 1, 1. Okay, for the apple. And how will you represent a banana? And the label, we also have to give the label associated with it. So let's say label associated with apple is +1 and with banana will be -1. Okay. So how do we represent the banana?
-1, -1, and oh,
Now it depends if you are talking about that weight could change slightly. So we can represent, I'm just assuming that both apple and banana are less than 100 grams. Okay. So -1, 1, 1. Texture is smooth. Okay. So these are our two patterns, 1, 1, 1, 1 and -1, 1, 1, 1. Okay. Now you have to design the perceptron for this. You have done the representation. Now you just have to solve this problem using perceptron. Okay. So how will you do it? Everything is done. So x1, x2, x3, and the bias initial weights are zero. You assume the initial weights that you have for the network are zeros, all zeros. So if in the problem the weights are not given to you, you assume all zeros. Okay. Then gradually the weights will change. Okay. Next, once this is ready, we follow the same process of solving the problem. So put the patterns here. So what are the patterns? The x1 and x2 values. So first is the apple, so all ones. And second is the banana. So that is -1, 1, 1, 1. Okay. And the desired outputs also. It is D is 1 for an apple, and -1 for a banana. So now what you need to do is just compute the net, the same procedure you have to follow. So just compute the net value. First case will be 0 because weights are 0. Next, so the output will be 1. Okay. Weight update will be 0. Okay. In the next case, it will be net will be 0 again, because see, there was a match, right? And what is the weight update equation here? It is plus minus 2cx, because we have used d as -1 plus 1. We can also use a d as 1 or 0. So in the case that it's an apple, it will be a 1. In the case that it is a banana, it will be 0. We can also use that, but I've used this, right? So the weight update will be plus minus 2cx. Okay. Now net value is 0, so output is 1. So now there is a mismatch. So I need to update the weight. So what is the equation that I'll be using? It will be minus 2cx, right? So d will be, d is negative, so it is minus 2cx. So assume c is to be 1. So c is 1. C is 1. So minus 2 times x, this vector. So it is minus 2, 2, 2, and 2. Okay. And next, what will you do? The same. This is the first epoch. First epoch is done, right?
मैम वो
So
डेल्टा डब्ल्यू उल्टा है शायद, 2 -2 -2 -2 है।
-1 है ना? -1. Okay, okay, okay. Yeah, yeah. It's a minus 2cx. Got it. Right. So again, I put the pattern here. This is epoch 1. Second epoch, put the pattern here. Put the weights. The weights were 2, -2, -2, -2. Find out the net value. What is the net value? -4. -4. So it is a -1. Now this is not able to classify. So what will you do? You will update the weights, but this time it will be plus 2cx. Okay. So it will be 2, 2, 2, 2. Okay. And what has happened now? This is your second pattern. So 2, 2, 2, 2. You add to this vector, that is 4, 0, 0, 0. And net value is again, net value is -4. So now this is matching. So can I say this is this particular network or these weights which we have got? What are the weights that we have got? 4, 0, 0, 0. Are they able to classify? Can I say that yet? Am I able to classify the patterns?
Yes.
Why do you say so?
मैम बिकॉज लाइक अगर वापस 1 1 1 आया तो 4 मल्टीप्लाई बाय 1 होके 4 हो जाएगा एंड वो हो जाएगा -1 आया तो
Hmm. So weights will not change, right? So third
यस यस
iteration also you will get the same weights. Weights will not change. And finally, so for for a complete iteration, if you get the same weights, then you can stop training. So when you're using the perceptron learning rule, when do we stop this training process? We stop this training process that when we get the in the same iteration, all the weights are same, then we stop. Okay. So because this rule is binary in nature, the output of this neuron is binary in nature. You'll get either 1 or 0. Okay. So you don't have a kind of an error signal like which is present in a continuous neuron. You don't have a continuous value. So at after some point, if the patterns are actually classifiable using a single perceptron, then the weights will become constant. They will not be changing. So that means that there are correct predictions always, right? For all the patterns, there are correct predictions. So you can stop at that point when you're going for perceptron learning. But the drawback of a perceptron learning rule is since it is binary in nature, so everything in terms of black and white, 0 or 1. So you don't have that flexibility of solving very difficult problems. Single neuron might not be able to solve it, right? Even a layer of neurons will not be able to solve it. But if you have multiple layers of neurons, then you can solve it. Okay? But the kind of rule that is used, it is the perceptron rule, but it is modified perceptron. When you go for a multi-layered feed-forward network, you go for a modified perceptron rule that is known as a continuous perceptron. It is known as a continuous perceptron. It's not a binary. The original model is binary in nature. Okay? So continuous perceptron rule we will see next time. We'll come to it. And that is required because a perceptron is not able to solve such problems, which are not linearly separate. So we'll just wind up today with the activation functions that we have. So what is the activation function? So you know that you are calculating every time the response of the network using an activation function. You apply a function over the net. What is net? Net is the weighted sum of inputs. That is called as the activation function. It is also called as a transfer function. So neurons which are placed in the same layer use the same activation function. There are two types of activation functions, linear and non-linear activation functions. So non-linear activation functions are the ones which are used in a multi-layer network. So that is what I was just telling you. So bipolar continuous or bipolar sigmoidal function. Okay. Range is between +1 and -1. Has a lambda, but lambda usually, so lambda decides the steepness of the sigmoid, but lambda is usually used is 1. Lambda is 1. So the equation actually becomes 2 upon 1 plus e raised to minus net minus 1. Okay. So that is a bipolar continuous which gives you the value between -1 and 1. Okay. So you can find that easily when you substitute the values of the extreme net values, extreme ends in place of net. So if you substitute net as minus infinity, if you're just looking at the extreme values, if net is minus infinity, what will be the value of this function? e raised to minus of minus infinity. E raised to infinity. What is e raised to infinity?
Infinity.
Infinity. So 2 over infinity is
0.
yeah. So 0 minus 1, right? So net will be minus 1 when net f of net will be minus 1 when net is equal to minus infinity. In the same fashion, if you apply net equal to infinity in this equation, what will you get? E raised to minus infinity.
For e raised to minus infinity, it basically become 2 minus 1, so 1. No, wait.
Yeah,
E raised to minus infinity is
0.
0.
E raised to minus infinity is 0. So 2 minus 1 becomes 1. So if you actually substitute the extreme values of net, you will get the range of this particular function. It will be plus 1 and minus 1. So all values that you will get will be in between plus 1 and minus 1, right? Similarly, unipolar continuous. So unipolar continuous is just this function shifted in the first quadrant, right? First and second. Okay. Everything, I mean, top, the top of that. So what you're doing is you're just shifting it upwards. So this equation, the equation for this is 1 by 1 plus e raised to minus lambda net. Lambda is assumed to be 1. Okay. So here again, if you just substitute the value as in minus infinity and infinity, you will get the range of this function, right? So e raised to minus infinity, minus of minus, e raised to infinity is infinity, right? 1 over infinity is 0. So the lower end is 0 for this function, and the higher end will be e raised to minus infinity is 0. So 1 by 1, that is 1. So 0 to 1. So that gives you the extreme ends of this function. Okay. In fact, these binary variants are you can just derive from these two functions. Okay. So as lambda tends to infinity in bipolar continuous, it becomes the bipolar binary function as it tends to infinity. Okay. Similarly, unipolar binary, you can derive it from unipolar sigmoid function, the sigmoid function. Okay. These two functions are called as soft limiting functions. The sigmoid functions are called as soft limiting activation functions because you have a range of values between those limits. Okay. You don't have hard values like 0, 1 values. And the other two functions are called as hard limiting activation functions. Okay. Because they are thresholding the values to either 1 or 0, minus 1 or plus 1. Thresholding is done. Next function is tanh function. What is the tanh function? What is the shape of the tanh function? You must have used tanh function. The tanh function again is a sigmoid function only. It's a variant of the sigmoid function. In fact, it's a scaled sigmoid function. This is the tanh and sigmoid plotted over the same graph. But they two are not the same functions. I mean, the argument to the functions are different. So it's a scaled version of the sigmoid. So the equation, for tan h of x is sin h of x by cos h of x, right? And what will you get the equation as?
E raised to x minus e
Yeah,
raised to minus x upon e raised to x plus e
yes,
raised to minus x.
yes. This will be in the numerator, this is in the denominator. So whatever I have plotted here actually is, since it's on the same graph, What this means is this has been scaled to this. Okay, so in fact, what is the relationship between tanh and sigmoid function? This sigmoid function, this is which sigmoid function, by the way? Which of the two it is? Should understand looking at the graph.
Bipolar.
It's bipolar. Okay, so tanh is a bipolar function, sigmoid also bipolar. Only difference is tanh sigmoid function is actually tanh of x by 2. So sigmoid, these are the exact equations which I have used for plotting these two graphs in Python. You can see the equations. First one is for tanh h. Tanh h, what I have done is 0.5x. The second one is lambda is 1 only, I have assumed. This is minus 1x. So what is the relationship between the two? Can you guess the relationship? It's translated actually. If you just rearrange, what is the equation?
They become identical.
This is the equation. When lambda is 1, this is the equation, right? If I rearrange this, what do you get? 1 minus
1
e raised
minus
to
e
minus
raised to minus x.
upon 1 plus e raised to minus x, right? So what is the and tan h, this is for sigmoid, and tan h that you have with you is e raised to x minus e raised to minus x divided by e raised to x plus e raised to minus x. Okay.
Divide numerator and denominator by e raised to x. And since it's 0.5x, instead of e raised to minus 2x, it'll become e raised to x.
In fact, this function, if instead of the argument being as x, if I write this, I try to find out tan h of x by 2, okay, then this term that I've written will be equivalent to this. Can you just rearrange this to get this now? If you divide this numerator and denominator both by e raised to minus x by 2, you divide, or you multiply this numerator and denominator by e raised to x by 2, won't you get this? Yes or no? I'm multiplying this with e raised to x by 2 and this also by e raised to x by 2. Aren't you getting this? Yes? Now you have got it. What is the equivalence? The equivalence is sigmoid function of x is the same as tan h of x by 2. Tan h of, instead of using the sigmoid function, it is a complicated formula. If you have tan h on the calculator, it will be faster. So tan h of x by 2 is the same as a sigmoid, bipolar sigmoid function with x as the argument. So if you want to find out the activation of a net value using the sigmoid function, right? So it is the same as finding the activation of net by 2 value using the tan h function. Is this clear?
Yes, ma'am.
Okay. That is the relationship between sigmoid and tan h function. Okay. Then you have this activation function. Others also are there. One such is ReLU. What is ReLU? is rectified linear units, and it looks like this. So the equation for this is basically whatever is negative, that is 0. Okay, and whatever is positive, that is equal to the output of ReLU will be the same. So ReLU of 5 will be 5, but ReLU of -5 will be 0. Right? Whichever values are negative, those will be thresholded to 0, and whichever values are positive, they will have the resultant will be the same. Okay. Now this ReLU function has been more popular of late, where it was used to solve the problems of which arose because of taking gradients. So you have certain problems when because the rules that we use for solving problems based on multi-layered nets, those rules, in fact, that rule is delta learning rule. That delta learning rule makes use of a continuous activation function. So those activation functions, when you're actually training them, it is not very simple. That weight update is not very simple. That R, the signal R, is not simply D minus O. No, it is not this. It involves a derivative term. It involves gradients. Okay. So because of that, what happens is many of these functions, as the training progresses, the gradient either vanishes or explodes. So there are some problems associated with training. So to encounter those problems in the intermediate layers, the ReLU function is suggested, which helps you overcome those problems. We'll come back to this function when we discuss deep learning. Okay, right now, we are not going to go into ReLU. Okay, used for some specific architectures because since the network becomes deeper and deeper, the number of gradients which are multiplied will be increasing, and if the gradients are very small, they'll be vanishing. If the multiplications will make the net, the output vanish, I mean this term R vanish. Okay. And as a result, what will happen? The weight will not change. Weight will remain static. In spite of you trying everything, weight will not change because of this problem of vanishing gradient. So this ReLU is used. We'll look at the mathematics later when we talk about deep learning. Okay. So this is one such popular function, and apart from this, there is a function called as softmax. I've not included that in the slide. Softmax. You have heard of softmax activation function? Softmax. It is used for a multi-class classification problem, multi-class classification problem. In fact, this softmax function is used as the last layer of a neural network because it gives you a probability distribution over the classes. So if there are 10 classes that you have for your problem, and there are 10 classes. So if, for example, you are classifying the 10 digit classification 0 to 9. So final layer that you have after the penultimate layer, this layer, softmax layer, is added, which gives you a probability distribution of all these over all these classes for the input. Okay, so one of these will have the highest probability, and that you will choose as the output of the network. So for example, you have given image of 6 as input to the network. There'll be a probability for 0, there'll be a probability for 1, 2, 3, all of these classes, each of these classes. But for 6, the probability will be high, say it is 0.99. Okay. And this you will choose as the classification for that. I mean, the output for this particular example that you have presented to the network. Okay. The softmax, in fact, it converts a range of numbers. If you are giving all numbers to it, it will convert it into a probability distribution. Sum of that will be 1. So whatever you're getting output, these are output probabilities. Sum will be equal to 1. Okay. So that also we will see when we look at multi-class classification. It is typically used in the output layer, this particular function. Okay. So these are some of the functions which are used, and some research papers you will find some combinations of functions which are used. They have proposed their own functions over several experimentation analysis that they have done. Okay? So that is also possible, but you need to go a lot into the math and the derivatives and all that to prove your function. You need to do a thorough experimental analysis for that. Okay? So we'll stop here. That's all for today. Thank you.